Sorry, I'm still chewing on my salad. Okay, I think this is where we start from. No. The slides and the text are not quite on. Well, no, this is example 4. We're starting on example 2. Okay. All right. Before we get going on that, though, last week the Vice President sent an email out, and for those of you who are not familiar with Lawson, we do some things in strange ways sometimes. So sorry about this, but this is what we're required to do. I was supposed to print off the email, and when I was reading the email, I didn't have a printer connected, and this morning I wound up having to help a student find a way to a special class that had just started. It was at a different building, and I didn't know where the class was or what the class was, and he didn't either, and I had to go around until I found someone who did know, so I didn't have a chance this morning to print anything. I was just trying to eat lunch. I didn't print anything then. But I'll tell you what it is. I know most of you are from other schools, and probably by this time, were any non-paid students still in the class? No. Okay. Is it first day of class or first week of class or something like that? Something like that. Here at Lawson, it's hard to say when it is, okay? And finally, the Vice President sent out an email, like I said, I think it was last week. I saw it last week. And it said that I'm supposed to read a certain text in class. I don't have it with me, so I'll just tell you what it is. If you have not completed payment by 5 o'clock today, you will be removed from the class today. We're almost at midterm. Thursday begins the second half term. So we're right close to midterm. If you haven't paid by the day, your name is going to be removed. Now, if you didn't bring the money today, I think all of you have paid, but I haven't. I enter attendance, and I really don't pay attention to those with asterisks by their names. But anyway, if you haven't paid, please do so today, or at least get over to the business office and explain to them what you're doing. And if you need to contact somewhere further up the line, they will let you know who you need to contact and let them know what your plans are. Because after 5 o'clock today, they're going to remove all non-paid students, unless they know the people are working things out. So I have to say that to every student who comes in now, so they'll all hear it. But and then Wednesday, again, how we do it here is so strange. I'm supposed to turn into the Vice President's office a list of paid students, and that's all the people that I'm allowing into the class, okay? And to me, why we have to go through the extra paperwork, it just seems like to me they'd say, you're out of the class, you're off Blackboard, you don't have access to anything anymore, you're out of here, okay? That'd be so much easier than going through all this rigmarole. But rigmarole we got to go through. So anyway, that's the major announcement I know about. Well, there is one other. I forgot to announce it to my first class this morning. Normally tomorrow I have office hours from 10 to 12, which I do tomorrow, and 3:30 until 5:15. However, tomorrow I still have those office hours, especially the 10 to 12, but as soon as I get out of my lab at 3:30, I've got to book it over to the Birmingham campus, and I'm on a committee to select a new biology instructor, and I've got to screen applications tomorrow afternoon from 4 until 5:30. So basically, I don't have any office hours in the afternoon. Technically, I'm over there, but you won't be able to find me because they put me off in a room by myself, or if anyone else is doing them late, I'll be over there doing that. from 3 to 5:30, and after 5:30 I'm getting out of there as soon as possible. But if I finish earlier, I'll be there until at least 5:15. But if I don't finish earlier, I'll get out of there as soon as I can. Okay, that's the only other announcement. I won't be in this office 3:30 to 5:15 like I normally would be. I'll be there 10 to 12, but not 3:30 to 5:15. Okay, any questions? Anything we've done so far? All right, we're picking up with example 2 on page 379. This is section 7.2, trigonometric integrals. And by the way, did everyone here get a copy of the first test? Okay, let me find that before I forget that. Whoops. I just went past it. Yeah. I think that's it. And on this, I think it's about two questions per section. But if you have any questions about it, I'll help you see that. It seems like maybe toward the end it's just one each. So anyway, that's the chapter. It starts, remember, 5, 6 or something like that, substitution method, and then it picks up with chapter 6. Yeah. Okay. So we're doing trigonometric integrals now, as opposed to the previous one. I'm sorry, this is not the right section, is it? We finished. I thought we were in trig substitutions. Okay, that's what I thought. I had my paper in the wrong thing. Let me get out of this. I put the roll sheet. I had it where we started last class, not where we ended it. So let's get that. I thought we'd got to be further in the chapter than that. So I think we're here on, I believe, page 388, example 4. Is that what y'all remember? Let's see if I can get this to come up from current slide. Okay, this is the one we're getting ready. Well, no, it's not quite. Does this seem right to you?
We just finished x squared over 4 minus x squared.
Right. Okay, that was example 4 at the top of page 388. So we're ready to do example 5. I think we did this. I think we covered this slide last time. Okay, this is integrals of this form. If you have a square root of x squared plus a squared, to me that looks like tangent squared plus 1. Okay, think of it that way. So let x be a tangent theta. Okay, if that kind of expression occurs in an integral, of course a needs to be greater than 0. You can't tell that it is there, but we will use that to be the case. Try this as a substitution. And if that's your x, then your dx is a secant squared theta d theta. And then if you then square this, add a squared to it, you wind up with a secant theta. Or if you take this and you draw a little triangle here, where that angle's theta, and the opposite is x and the adjacent is a, then this up here is going to be square root of x squared plus a squared, and that will be secant of theta will be the hypotenuse over a. So either way, you wind up with that. Sorry, still got veins in my teeth, salad in my teeth, so sorry. Okay, so let's do example 4. Now, the figure here is not for example 4, okay? We're going to have to do that. That's the old edition. We probably just skip that altogether. But here's example 4. Evaluate this. Yeah, let me get my pen set up. Evaluate this integral 1 over the square root of x squared plus 9 dx. Okay. Now, try as you might, I don't think you're going to get a regular let u equal something substitution not going to work. Because if you let u equal this, which would be the innermost part or the most complicated part of the problem, that would be 2x x squared plus 9, then du would be 2x dx. There's your dx, but you can't get a 2x anywhere out of that. So regular substitution won't work. But this is one of those of the form square root of x squared plus a squared, where a would then be what? 3. Okay? Well, sorry. What substitution do we use then? Second? Yeah, we let x equal 3 tangent theta. Now, what's different about this? Remember, in the other substitution, you come up with a new variable to be some expression in this. Now you pick the variable here and let it be an expression of theta, or of some trig expression. And that's what we're going to do. And if we did that, let x equal that, then what? Dx is equal to secant squared x, right? Secant squared theta. D theta. Okay? Dx would be that. Now, you don't have x up here just by itself. You have an x squared. So what would x squared be? Square that. 9 tangent squared theta. But you don't just have an x squared, you have an x squared plus 9. So x squared plus 9 would be 9 tangent squared theta plus 9, which you can do what to? Factor out a 9, and that leaves you with a, whoops, I probably am cheating, skipping steps, sorry. 9 times tangent squared theta plus 1. And what's tangent squared theta plus 1? Secant squared theta, Pythagorean identity. So it's 9 secant squared theta. And the square root of that, because this is x squared plus 9, you have the square root of that. So the square root of this would be the square root of this. And what's the square root of that? 3 secant theta. All right. Now, the other way to arrive at that is draw your little triangle here. Okay? Now we said let x equal 3 tangent theta, which then would imply tangent theta is equal to x over 3. If you divide both sides of this by 3, right? And tangent is or, in terms of the sides, opposite over adjacent. So this would be x over, and this will be 3. If that's your theta, tangent theta would be x over 3. And this up here would be x squared plus 9, right? Which is the square root of x squared plus 9. That's exactly your argument here. But in terms of theta, all right, here is Khalil. There you are. required to say this to the whole class, and since I already said it, the rest of them got to say it again. I got an email from the vice president. I saw it last week about I was not where I had a printer attached to my computer, so I couldn't print it. I'm supposed to read the email, but I can't. But here's basically what it says. So if you know of any students who fit this, classmates in other classes or anything, please let them know about it, especially Tuesday, Thursday classes, because they won't have a chance to hear it. And here's what it is. They are going to remove all unpaid students from the rolls at 5 o'clock this afternoon. Okay. So if you know of anyone who hasn't completed payment yet, please tell them to get in touch with the business office today before 5 to let them know what the plans are. I know some schools like yours had to transfer some funds and stuff. Do you know if that's been completed or? Okay. You might want to check and see. I could check, so if you, they might better be easier to get them to find it in the either registrar's office or financial services. And if not, be sure let someone know in the business office what the situation with it is. Because I know it's coming, but yeah. Okay. So, but let anyone else you know, especially those in Monday and Tuesday, Thursday classes, because that's going to happen before tomorrow. Okay. All my Tuesday, Thursday classes who the students have been here, they have paid. Those who haven't been here, I couldn't announce it to them anyway. Okay. So here's what we've got. If you had tangent theta is equal to x over 3, and then you had this thing, if you think about it, secant theta, or what secant theta was? Not opposite, adjacent, because it's 1 over cosine. So it's adjacent. Hypotenuse over adjacent. So secant theta would be tangent of x. So secant theta is equal to the square root of x squared plus 9 over 3, and then multiply both sides by 3, and you get 3 secant theta is equal to the square root of x squared plus 9. Okay, we've got this written every sort of way that we can here, so let's change our integral. And here we go again. Okay, glad you're here, but I need to repeat this again. Sorry about it, folks who are here already. Last week, the vice president sent an email, or I saw the email last week. I can't remember what it was dated. But the vice president sent an email. We do things strangely here at Lawson. We let people be in classes for close to half the term, and then we say, you got to pay now. Yes. So if you haven't paid already, please get paid, or at least get in touch with the business office before 5 o'clock today. My memory is most of you are paid, but it's been a while since I entered your group attendance, and I don't even remember then whether you had an asterisk by your name or not. But if your payment hasn't gone through yet, be sure you get in touch with the business office and let them know what the status is, because otherwise at 5 o'clock today you'll be removed. So, and one reason I'm telling you this is that if you have any classmates or friends or other things that are here who haven't finished paying, be sure to let them know, because I won't see the Tuesday, Thursday folks until tomorrow, and 5 o'clock today will have already passed by then. So let them know, get that completed by 5 today, or at least get in touch with them by 5 today to let them know what's in the works. Okay. We're doing example 4, bottom of page 388, chapter 7, section 7.3. Okay. There was our problem. What's the new integral based on what we have here? It's the integral. Your dx is, I'm going to put the 3 on the outside, 3 secant squared theta d theta. That's going to be instead of the dx. There it is. Okay? Over the square root of x squared plus 9. And we did this one way here and another way here. Both times we wound up with 3 secant theta. So divide by 3, the 3's go away, and this is dividing by secant theta. Well, secant theta and the secant squared theta is just secant theta, and you simply have the integral of secant theta. Now, we did this before in the last section. Does anyone remember what the integral of secant theta is? And if you don't remember, you can just look it up. Back of the book, or turn back in the text to the table at the end of section 7.2. In my book, it's 383. You may have slightly different pagination depending on what version of the book you have. But there you see that the integral of secant theta is, anyone see it? Natural log ln of absolute value secant theta plus tangent theta. Of course, you know when it says x and you got thetas, just change it to thetas, plus tangent theta, and then you got your plus c, right?
It is a plus, it's not multiplication.
Say that again.
It's plus, not multiplication.
The log of secant x plus tangent x, right? Is your book not right?
No, this from the problem board there that I must have written.
Okay. No, secant x plus tangent x plus c. Okay? That's a log there. It's pretty ugly. But now we need to get back to x's, because the problem was given to us at x's. Why give the answer in the theta? Here we go back to our handy-dandy triangle again and see what secant theta is. Secant theta, we saw, was right here, the square root of x squared plus 9 over 3. So this will be the log ln of absolute value of the square root of x squared plus 9 over 3 plus tangent we already had was x over 3. Okay? Now, we don't know what x is. Okay? We don't know if it's a positive number, a negative number, or what it is. So we leave the absolute values on there. Now, if we were only concerned with this one, we could lose the absolute value, because this is a principal square root, meaning positive square root, over 3. That's going to be never negative. So you take the log of that. Let's see. Well, no, maybe. Well, I guess we just assume it's not going to be 0. Something's not going to be 0. But because we don't know the actual value for x, we'll leave the absolute values on there, and then change this to leave our plus c. So that should give us the answer that they got. They may have dropped the absolute value, we'll see. No, okay? But they do this. That's the same as the absolute value of square root of x squared plus 9 plus x, because it's already over common denominator over 3. And if you recall from rules of logarithm that this is the log of absolute value of x squared plus square root of x squared plus 9 plus x. I'm sorry, I already had the absolute value there. Got too many absolute value bars. Okay. Minus the log of 3 plus c, right? But guess what? Log 3 is just a number. So why not incorporate that into our constant? And that's what the book did. So their final answer was log absolute value, the square root of x squared plus 9 plus x minus plus c. Okay. Now that's a different c from our original c, but it's still a c. Okay. Now, and again, if you knew a priori that either x was always positive, or that, you know, this is already guaranteed to be non-negative. It could be 0. No, this could be 0 either. So as long as this wasn't 0, or wasn't negative, then this whole phrase would be positive, then you could lose the absolute value bars. But if you don't know that, it doesn't hurt to leave it. All right, any questions about that solution? All right. The last of our trigonometric substitutions will involve expressions like this. Now I'm going to have to, if I go to right, I've got to lose the zoom real quickly. But for now, let's look at it. If you had this form, the square root of x squared plus a squared. Now let's just think back. The first form we had was the square root of a squared minus x squared. What substitution is that? Actually, you could do either sine or cosine. Most of the time they do sine. So it keeps the SIG and sine's better, okay? So the sine, because if you think about it, sine and cosine are related by 1 minus x, the other squared. So that's that. When you had a plus in here, that's what? Tangent. And when you have the x squared in front of a squared, so x squared minus a squared, what would that be? Secant. Okay? If that form occurs, the square root of x squared minus a squared, not a squared minus x squared, that's sine, x squared minus a squared, then we use secant. And if that occurs in an integral where a is greater than 0, but of course you can't see that because this is usually going to be a positive number. I mean, it will be a positive number. Try the substitution, see if it works for you. And here's why. Because in your dx, what is the derivative of secant? Yeah, now there's your product. That may be where you got crossed up before. Derivative of secant is secant x plus secant x times tangent x. The integral of secant x is secant, the log of secant x plus tangent x. Okay. So that's your dx. And if you started doing the same manipulations we did before, square this, a squared, secant squared, minus a squared. Factor out an a squared, you have secant squared minus 1. What is secant squared minus 1? Tangent. So that would be the square root of a squared. That would be a. Tangent squared would be tangent. So you would have a, this square root here would be a tangent. Okay? And we'll see that with the triangle too. So both ways will work. All right. Let's do example 5. It looks like the same one. So let's evaluate this one. The integral of dx over x squared times the square root of 4x squared minus 36. Now wait a minute, time out. That doesn't look exactly like the others have looked, does it? What's different about it? Number one, you got x squared out in front of that radical. Don't sweat it. Let's just see what happens. Okay? That's another thing you notice though. It's not just x squared minus a squared. It's ax squared minus b squared or something like that. So what are we going to have to do there? At least step one. Yeah, pull a 4 out, okay? So this will be factor a 4 out, I guess would be a better way to say it. The integral of dx over x squared, don't mess with that. But let's take a factor out a 4 out of that, but pull it out of the radical, what does it become? No, the square root of 4 is 2, okay. So the 2 comes out, and then you have the square root of x squared (9). Exactly. Okay. That now is of the form without the x squared there. Now this 2, I would take it all the way outside the radical, but it's in the denominator, so make sure it's a 1/2. Okay. Now I think we're ready for our substitution, and what did we decide that would be? X equal. Yeah, we're going to get to the x squared in a minute, but let's start with the x. What's that substitution? 3, because that's your a, the square root of a squared. 3 secant theta. Okay. Then our next step would be dx would be 3 secant theta tangent theta d theta. Have to have d's with d's. Okay, let's start doing our other stuff. And one of those other things is going to be, they don't really have x's up there, they have x squared. So what's your x squared? 9 secant squared theta. Okay. And then x squared minus 9 would equal 9 secant squared theta minus 9, right? Which would then be 9 times secant squared theta minus 1, which would be tangent squared theta. But this x squared minus 9 that you have here is really under a radical, so put it all under a radical, and that would be 3 tangent theta. Very good. Now we're ready to plug and chug, I think. So our new integral, is equal to 1/2. That 1/2 is there from our factoring out the 4 from the radical. Okay. The integral of, and what's that dx again? 3. So I'm going to put the 3 on the outside. Secant theta tangent theta d theta divided by, what was my x squared? Okay, let's put the 9 on the outside too, and this will be a secant theta, secant squared theta. And what was my square root of x squared minus 9? What did it wind up being? A 3, so this 3 will divide out that 3, so that'll leave you just a tangent theta. Whoops, okay, started to put a d theta there. We don't have a d theta down there, we never do. Okay. All right, I think we got it all plugged well, didn't we? So, from my observation, it looks like a 1 over 18. And this secant will divide out one of those. The tangent will divide out the tangent. And it looks like we have 1 over secant theta. What in the world is 1 over secant? Say again? Cosine. That'll be cosine theta d theta. And I think I can even do that. What is that? Say again? Did someone say? Sine. Sine theta. And then we can do our plus c. Okay? But we're really not interested in what the thetas are. We need to go back. And by the way, let's time out again. Did they do the triangle right? They said let x equal, we said let x equal 3 secant theta. Therefore, secant theta is equal to x over 3. And remind me what secant theta is. Adjacent, is that what you said? Yeah. Hypotenuse over adjacent, so this would be the hypotenuse, and that would be the adjacent. So those are right for that theta, and that 90 degrees. So then by the Pythagorean theorem, the extra side over here would be the square root of x squared minus 3 squared, which is this one. And so I think we got everything we need. And then let's look back at it and see if your 3 tangent theta is equal to the square root of x squared minus 9, like we said. Tangent theta is square root of x squared minus 9 over 3, so multiply both sides by 3. Yeah, everything works out very nicely. But now we're interested in sine theta. With this triangle, that's the triangle we got. There's the theta we got. What is your sine theta? The square root of x squared minus 9 over, second, not 3. Sine is x, opposite over hypotenuse. So that seems to be our answer. Plus c, of course. Okay? Does that make sense? And then once you have something in the denominator, they write it as the square root of x squared minus 9 over 18x plus c. Doesn't matter. Either way is fine. Just to get it in the same form they have theirs. Any questions on that? So you see that x squared out in front? That didn't hurt us. We had to calculate what x squared was anyway. Throw it in there, see what happens. Okay. Now, that introduced a little wrinkle in that you didn't have an x squared minus a squared to begin with, but you could factor out whatever your coefficient of your x squared was, take out the square root of that of both terms, and go from there. But so far we have dealt only with expressions of x squared plus or minus a squared and a squared minus x squared, all in the square roots. Now, remember the good old completing the square? Yeah, if you were like me, you thought, oh, I hope I'm through with this. But no, you're not. You know, it's going to keep popping up its ugly little head every chance you can. So what happens if you have the more general form than one of those specific ones of the square root of ax squared plus bx plus c? What are you going to do with a situation like that? Let's see. Okay? Well, ignore the square root here. What does that look like to you? looks like the standard form for a quadratic equation, okay, not in the function mode, but in the equation mode. And then we use this quadratic formula. How did we derive the quadratic formula? Do you remember that? It was really a lot of fun back when we did it. Do you remember how that went?
Did we use the Pythagorean theory?
In really a roundabout way, perhaps. But actually, what we did was complete the square of this. That's how you got the quadratic formula, because you did minus b, remember, plus or minus the square root of a. You did this. If you were completing the square, the first thing you do was factor out the a, and then out of both of these two terms, and you keep going, and you finally wind up with the quadratic formula. Well, similar here, we're going to complete the square. So let's go to an actual problem and do it. Can I erase this right here so far? Okay. And let's do this one. Oh, wait, let me just make sure they don't have a slide for it. Oh, they do, don't they? Good for them. Okay. All right, here is the one we're asked to do. Sort of forget the second part of that, but here's the first part. We're asked to integrate dx over x squared minus 6x plus 11 squared. Okay? Now, that sure doesn't look like a square root of ax plus bx, ax squared plus bx plus c, but it is that form. Okay? Now, what we're going to do is do a substitution that makes that a perfect square. Okay? And what we're going to need to do is complete the square to get there. Okay? So, let's start with it. Do you remember how to complete a square? I'll have to shrink this back. Let's start with x squared minus 6x plus 11. Forget about the square part. We'll get to that later. How do we make this? How do we complete the square on this one? I'll tell you what I do. I write the first two terms down. X squared minus 6x. Then I put a blank before I put the plus 11. Now, why do you reckon I did that?
You gotta make sure that you're going in descending order. Isn't that right?
Something like that. I want this to be a perfect square. That's what we call it, completing the square. I'm going to let that, whatever happens to this, happens to it. So I want this to be a perfect square. Remember how to make that a perfect square. That's why the blank's there, so I can make it a perfect square. Take half of the negative 6, and then what you do with it? Square. Okay? Very good. All right? Now, while I'm doing that, I'm going to write it down because I want this to be a perfect square of x. And when I take half of the minus 6, that's going to be a minus 3. I'm going to put it right there and square it. That's going to be my perfect square. Take half of negative 6, that's negative 3. Square it, that gives you plus 9. Uh-oh, we've changed the problem, huh? Yes, that's exactly what I was going to say. I've just changed the problem because that's 9 more than my original one was. So over here, I have to subtract the 9. Now it's the same problem I had before. It just looks strange, okay? So this is indeed x minus 3 squared, right? This becomes plus 2, right? And guess what? That is the same thing I had up there. If you don't believe me, square that binomial. That would be x squared minus 6x plus 9 plus 2 is plus 11. Yeah, it's the same thing. But it's written as a perfect square plus something else. Okay? Now, that form of a perfect squared plus something else, what kind of substitution was that? Just did it a little earlier today. First one we did today. Tangent. Okay. And what was the A? It was the square root of that thing, right? Before it was always a perfect square, if not, so it becomes the square root of 2. So that's our new A. So our substitution here is let, okay, now get this, remember it's our x minus 3 is equal to the square root of 2 times tangent theta. Okay? Then, and by the way, yeah, this is the equation down here. Don't lose track of that. Okay? In fact, let's back up one. I sort of don't like doing this because it introduces so many, but since they're doing it, let's go on and do it. Okay. After a while, you just get tired of too many substitutions, but here's what they're going to do. Let u equal x minus 3. Okay? Then, what's your next step? Second? Du is equal to dx. Got it. Okay? So now we got our du equal dx, so we can change this, okay, to the integral of the dx is du, and this thing in here we see is u squared plus 2 squared. Okay. I wasn't going to put that step in, I was going to go straight to the other, but since they have, let's go on with that. Now we do our tangent substitution. Let u equal square root of 2 tangent tangent theta, sorry. Again, so many substitutions, it's easy to forget which one you're working on. Okay, so that's going to be our sorry, substitution, the trig substitution. What's the next step in this one? Then what? Du is equal to square root of 2 secant squared theta d theta. Very good. Alright, let's see where that's led us now. Now, you can either go back and do your u squared plus 2 and do all that stuff, or you can draw your picture. To me, drawing the picture is helpful. Okay? This implies that tangent theta, yuck, this board collapses on me. All right, let me try that one more time while I'm holding it. That tangent theta is equal to u over the square root of 2, right? Divide both sides here by root 2. Okay? Now let's draw our little picture. If this is angle theta, what is tangent theta? Say a little louder.
X minus 3.
I'm sorry, I can't.
X minus 3.
Okay, yeah, we're going to get back there, but for now, let's call it U. U is the opposite side. Tangent theta is opposite over adjacent, so U over root 3. Root 2. What am I doing? And what would be your hypotenuse then? The square root of U squared plus root 2 squared, which would be plus 2. Right? You see that? Oh my. Wow. Now, let's continue. And that's almost a little problem here, but we'll deal with it in a minute. Okay. Let's not get lost in where we're going here. So let's start plugging in this integral here. This is equal to the integral of your du is, let me leave a little more room there because we've got some stuff to pull out. The integral of du is a square root of 2 in the numerator here, a secant squared theta in the numerator there, d theta in the numerator there, over, now, looking at our triangle here, what we have is secant theta is equal to the square root of u squared plus 2 over the square root of 2, right? By that? That means that secant squared theta is going to be u squared plus 2 over 2, right? So that means that 2 times secant squared theta is equal to u squared plus 2. Right? Everybody see that? Okay, well that's your denominator here. That u squared plus 2 is 2 secant squared theta, but then you're squaring that, so it'd be 4 secant fourth theta, right? Okay, so that will be a 4 down here, and that thing will be secant fourth theta d theta. All right. You know what? I think they've done a lot of work for us, but I think it's better for us to do it ourselves. Okay? So what does this become? Root 2 over 4. Secant squared goes out, and leaving you a secant squared down here. And what's 1 over secant squared? Cosine squared. So this will be the integral of cosine squared theta d theta. Okay? But I don't know if you remember the integral for that. Let's go back a couple of slides here. More slides than I thought. Nope, sorry. Oh, sorry, that was when I was on the wrong section. Nope, that's not it. There we go. Okay. If you don't remember what that integral is or how to get it, again, turn back just a few pages and see what the integral of cosine squared is. You see it? Now they give two different forms. One has a 2x, sine of 2x in it, and the other is in terms of sines and cosines. I think I prefer the one with sines and cosines only, not with 2 theta in it, 2 x's in it. So let's use that form. So this will be the square root of 2 over 4 times x over 2. Okay, that would be theta over 2, right? Follow along here. Plus 1/2, and it says sine theta cosine theta plus c. Now, I put the parentheses in there for a reason. I wanted to separate it out from the plus c, and you got the square root of 2 over 4 multiplied by everything. What we've got to do now is figure out three things: what theta is, what sine theta is, and what cosine theta is. And in every case, I would go to this triangle. Except, yeah, we are going to express this in terms of u's, right? So, what is theta in terms of u? Well, let's get the simplest thing we can do here. And it's right here in front of us. Here, okay. Tangent theta is u over root 2, right? That puts theta to be inverse tangent of u over 2. So let's get that down. So this will be theta equal the inverse tangent of u over 2. Okay? Or u over root 2, I'm sorry. Alright. So, this becomes, you know what, I'm going to pull out that 1/2 too. Okay? The square root of 2 over 8 times inverse tangent. Now, y'all were wanting to do this a little bit earlier. Somebody was. Let's go on and do it now. You see the u is simply x minus 3, right? So instead of u, we're going to put this x minus 3. So this will be x minus 3 over root 2. No, yeah. Okay? Got that part? Plus, now I already pulled the 1/2 out. Made it an 1/8 on the outside. Done with that. Now let's go back to our triangle and see what sine theta is. This is theta. What is sine theta? U over this, right? So let's write it down, but not with u's. Let's write it with x minus 3's. So that would be x minus 3 over the square root of, well, now this thing right here, don't you know that's exactly what we started with, right? This thing that became u squared plus 2 is exactly this. So let's go on and put that substitution in too. X squared minus 6x plus 11. Okay? So that's your sine theta. What's your cosine theta? Second, square root of 2 over that same thing. So then this will be times the square root of 2 over this thing here, 2, the square root of x squared minus 6x plus 11. Okay, now notice these things are multiplied here. After that plus sign, they're multiplied. So, let me clean up my answer a little bit here. This will be the square root of 2 over 8 times the inverse tangent of x minus 3 over root 2, okay, plus, now, we had a square root of 2 over 8 out front here, and we're going to introduce another square root of 2. So square root of 2 times square root of 2 is 2. 2 over 8 is 1/4. So our fraction in front of this part is going to be 1/4. Okay, and folks, by the way, I've been leaving off my plus c's, but you can go on and put them all back in there. You know, wherever you need them, put them in. Okay, 1/4. And we pulled the root 2 out to do that. So this is going to be an x minus 3 over, and here we have the product of the same two radicals, square root of the same thing. So this is just simply going to be x squared minus 6x plus 11. Okay, and then we can put our plus c out there. Okay. So that, I think, should be the final answer. This coefficient, which came from all over the place, root 2 over 8, inverse tangent of x minus 3 over root 2, plus, and then 1 root 2 is going to multiply by another root 2 and give us a 2 over 8, which is 1 over 4, and you had the x minus 3 over the product of those radicals, which is just, and the same radicals, so it's that, over plus c. So, let's see how far off we are from their answer. Hopefully not far. Okay. Now, they wrote their coefficient that what I was writing is root 2 over 8. They wrote it as 1 over 4 root 2, which of course if you multiply numerator and denominator by root 2, that would give you root 2 over 8 root 2. Root 2 is 2, that would be 1 over 4 root 2. That's the same part. Inverse tangent of x minus 3 over root 2, got it. Plus, and I put the 1/4 on the outside, they drug it on the inside, x minus 3 over, and they put 4 times x squared minus 6x plus 11 plus c. Yeah. Same thing. Only difference is how they express that. And you know, most of the time in math they say don't put radicals in the denominators, and they wouldn't put it in the denominator. I like this form a little better. This one we can't avoid too easily. I mean, we could do root 3 times this over 2, but that really is messy, so let's leave that alone. This one, they did pull the 4 in here, into the denominator here, and leave off, so I'll do that just to satisfy them. It makes no difference. It's the same form. So we'll erase this and extend this line here so we can put the 4 there. Same deal. And in so doing that, they left off these parentheses too, because it wasn't really helping anything. All right, that is the last exercise in this, or example in this section. but they're going to do some of the math here, so we'll compare it to what we did. We did the first part exactly the same. Pretty close. They didn't show all the steps. But we did show all these, pretty sure. Okay. There was our original u is equal to root 2 times tangent theta, or tangent theta is u over root 2. And then the square root of u squared plus 2 was the square root of 2 secant theta. Our du is, from here, is root 2 secant squared theta d theta. Got it. So this integral, we did this, is du over u squared plus 2 squared would be du was root 2 secant squared theta d theta times 4 over 4 secant 4 theta. They skipped a few steps to get there, but that's basically the same thing we got. They pulled out the 1 over 2 root 2, I think we wrote it as root 2 over 4, integral of cosine squared theta d theta, and then they rewrote that as 1 over 2 root 2 times theta over 2 plus sine theta cosine theta over 2, which is the same thing we did, maybe in a slightly different form. And that's where we put in our plus c for the first time. I don't know if, yeah, here's a triangle, which you'll see is just very similar to our triangle. There's theta u over root 2 and square root of u squared plus 2 there. And then the integral of that, this is our original integral, I think. Okay. What I did, as I mentioned earlier, was cram down my salad, and I didn't really drink anything. I was so busy eating a salad. So now my throat is so dry, I can't talk. My eyes are dry, everything's dry. So try to get through this. So going back to what we had, this was our original integral, not quite the original. We did u substituted for x minus 3, I believe it was. And that became this and this and that. Okay. And that became this, inverse tangent of this, plus that, plus c. And when you do your substitutions, they substituted differently in different order, but it came out the same answer. Okay, we've already checked that. Now, this is in the summary, a review of what we were just doing, these trig substitutions, and I don't say memorize them, but recognize them for what they are. This is a sine form. Constant minus x squared, that's got to be a sine. So this constant, whatever the constant is, the square root of that constant times sine. That's your substitution. That makes the dx, and this is where sine is advantageous over cosine, dx would be a cosine theta d theta. Whereas if you had chosen x equals cosine, which is perfectly fine, then you have dx is equal to minus a sine theta d theta, which that minus sign is a lot easier to trip you up later. Okay? And then when you go back and plug this value x into this expression, or draw your triangle from here, either one, you'll get that this is a cosine theta. Okay? Now, if you have the plus in the middle, that hopefully reminds you of tangent. Okay? So a x is equal to a tangent theta do your dx, a secant square theta d theta, and your square root of that, either by plugging these values in here or by drawing a triangle, you'll get that a secant theta is equal to that square root. Okay? And if you had this form where it's a squared minus a squared, then this is going to be secant theta, because secant squared minus tangent squared is equal to what? Gracious, I actually got something there. Okay, so that should be the key that you use x equal a secant theta. Dx is at a secant theta tangent theta d theta. And then when you go back and plug all those in, you wind up this expression being a tangent theta. Now, don't let this throw you. But if you notice, if you let this be the substitution here, then this becomes what you're that. If you let this be your substitution here, this thing becomes that. So you've really just exchanged these two expressions, okay, in a sense. They go that way. That first one just pans out the way it does. All right. Do y'all want to do, oh wait, here's your triangles that represent those same three radicals. Okay? That's why my throat is so raw feeling. Okay. And that first one, when he said let x equal a sine theta, what I like to do is divide both sides by a. Sine theta is x over a. Well, sine is opposite over hypotenuse, x over a. Does that make this other side the square root of a squared minus x? And that becomes your cosine. A cosine theta is equal to this. So that's where that comes from. When you have x equal a tangent theta, again, divide both sides by a. Tangent theta is x over a. Tangent theta is opposite over adjacent, so x over a. That makes this side over here square root of x squared plus a squared, exactly that, and that makes the secant theta is hypotenuse over adjacent. Okay. Okay, so that makes a secant theta equal to this. Okay. Similarly here, when you have this kind of a form, the substitution of x equal a secant theta, meaning secant theta is x over a, which is hypotenuse over adjacent. And then if you, the third side by the Pythagorean theorem would be x squared root of x squared minus a squared. That would be that. And then when you look at that, that becomes tangent theta. Well, it's tangent a times, tangent theta is this over a, so a times tangent theta would be this part here. So those two just sort of interchange the pluses, but because they're hypotenuse, that's the minus that becomes your opposite side. Okay. I think that's all. Now, yes, it is. Okay. Y'all like to do preliminary questions or not? Not? Okay, do it. State the trigonometric substitution appropriate to the given integrals. Here's the first one. The square root of, the integral of the square root of 9 minus x squared dx. What would be the substitution you use? X equal, and what's your a here? 3 sine theta. Very good. Okay. The B one here, they don't say anything, do anything with it, just state the substitution. Here's the B one, the integral of x squared times x squared minus 16 to the 3 halves power dx. All right. Wow. I may have to take a break and just go get something for my eyes. Let's see if we can keep trucking here, because we've already been at it an hour and 25 minutes. But that's about halfway through, isn't it? Yeah. So we might take one. Let's see if we can get these done. What trig substitution would you use? Say again? Secant, okay. Let x equal four secant theta. Okay? Now you're going to have some mess to do with it, but that's the substitution you use. This is your a squared, so the a times secant theta. Got it. Let's see about c. The integral of x squared times x squared plus 16 to the 3 halves power. What will you do there? Let x equal, second, 4 tangent theta. Excellent. Okay? And the D one here, the integral of x squared minus 5 to the minus second dx. Square root of 5 secant theta, exactly. Okay, good deal. Let's just make sure the back of the book got them right. I think they should. Sometimes they screw up. This is 7.3 preliminary exercises. X equals 3 sine theta, 4 secant theta, 4 tangent theta, and the square root of 5 secant theta. Good for them. Okay? How about number 2? What if you were given this integral? Integral of x times the square root of 9 minus x squared dx. What would you use there? Say again? What's that? Okay. That wasn't there? Yes. That was a square or a cube or anything else? Yes. Guess what? Good old U substitution. Because U is equal to the innermost part, the most complicated part of the problem, 9 minus x squared. If U equals that, then du would be a minus 2x dx. Here you have an x dx, do it 1 over minus 2. Yes, don't go through that if you can get around it. Always look for the simple substitution first. These others just didn't work because you either didn't have x in front or you had x squared in front. Okay. Now, here is a strange thing to ask for, but we'll do it. Express sine of 2 theta in terms of ITOs, in terms of x equal sine theta. Okay? Express the first thing, sine of 2 theta, in terms of x, where x is equal to sine theta. Where would you begin? Okay, excellent. What is that? Sine of 2 theta is equal to, say again? How about 2 sine theta cosine theta? Is that right? Yeah, remember from, yeah, that's it. Okay, there's my x right here. But cosine theta is not in terms of x. So how can you get it in terms of x? Take this right here, draw your little triangle. These are so helpful. Let this be your theta. If sine theta is x, what is it? It's what? Okay, this would be x over 1, right? Opposite over hypotenuse. So this side down here would be the square root of, what were you saying? 1 minus x squared. And what's cosine theta then? Over 1, okay. So this would then be sine of 2 theta would be 2x times the square root of 1 minus x squared. Okay? Let's see if that's what they meant in the back. I'm pretty sure it is. 7.3. They didn't do number 2, so I'll just tell you that is right. And number 3 is 2x times the square root of 1 minus x squared. Good. Now they don't have the answer for 4 in the back either, because for some reason they're only doing odds here. But let's do number 4. I'm going to erase what we got so far. Okay. What it says here is draw a triangle that would be used together with the substitution x equal 3 sine theta. I'll draw a triangle. I'll even put the theta in. You tell me what to put where. I'll call this hypotenuse, I'll call this opposite, and I'll call this adjacent. You give me an expression for each of those 3 letters. Hypotenuse is 3. Is what? X. You got it? How about 9 minus x squared? Right? Because it's the square root of the square of the difference in the square of the other 2's. Got it? You see how that works? Now, what I like to do first, it just makes it easier for me to see, divide both sides by 3. Sine theta is equal to x over 3. Sine theta is opposite over hypotenuse, x over 3. And then the third side, easy to get. Okay, good deal. Homework exercises here in 7.3. Do 1 or 3 or both. Do any of the any of the odds 5 through 9. Do 11 or 13 or both. do any of the odds 15 to 31. All right, now 33 is a little proof, which you could do or not. Probably wouldn't be a bad exercise to do. And or 35. So I'll say 33 and or 35, one or both. Then do any of the odds 37 to 41. And either, 43 or 45 or both. Then do any of the odds 47 through 53. I'll let you decide how many. Further insights and challenges, I don't see much there that I could think of for a paper topic, but if you want to try either of those, go for it. Okay. No, actually just 55 is the only one there. All right. If you don't mind, let me take a real quick break. I got to go get something to drink because my throat is so sore and raw right now. All right, any more questions on 7.3? All right, now some of you, most of you are from other schools other than Lawson, and I've got a question for you as soon as this ends here. And I assume all of you had your Cal 1 at your home institution or somewhere other than Lawson. I know at least one or two of you are Lawson students. But here's the question I have for you, for those from other places especially. Did y'all focus on hyperbolic functions, trig functions? They're not really trig functions, they're hyperbolic functions. They call it sinh and cosh and stuff. I don't know why they still do this. To me, it's they're sort of artificial functions, and in some ways it's sort of a handy thing to think of, but really they're all expressible in terms of exponentials, and to me exponentials are far easier to work with than hyperbolics. Now, they have nothing to do with sine, cosine, tangent, or anything else. However, their relationships with the derivatives and antiderivatives or integrals are similar, but just enough different to screw you up. So why mess with them? Just stick with the exponential forms, and then all the signs will work out. For instance, if you'll notice, if this was sine and cosine, that would not be right. You would need a minus sign here. That one would be right. Okay. This one would be right. This one wouldn't be right because you would need a plus sign here. And I don't even mess with those anyway, but these two would be all right. But see, whether the sign's right or wrong, you have to keep up with that. Why not just use the exponential function that they're derived from and go from there? To me, it's much easier. Maybe I'm just weird, but I do. So if y'all haven't done them before at your school, I see no reason to do them here. If by chance in upper level courses you might run into them, I'm just going to give you the slideshow so you can always go back and see what they are. But that's all we're going to do. We won't even work any examples with them. I'll zoom in on them so you can see. And because you have these other forms, but guess what? We already have a form for that. So why come up with a hyperbolic substitution when we already have a tangent substitution that works perfectly well? Okay? And on this one, secant, a secant theta works perfectly well. Why introduce a hyperbolic form? Okay? So I don't see the point in it, okay? That's just part of either a solution or a, yeah, I guess it's just part of a solution since we're not doing the problem. Let's go on. Here they give them to you again. If by the way you never use the hyperbolics, why would you ever use the inverse hyperbolics, okay? But if you ever need them, here's what they are. And you see they differ enough from your trig functions that, again, they just get really, I don't even like to compare them, okay, because they just throw me off on the sides. Now, when you get to these two down here, that may be the only way. Nah, I think even the substitutions we already know probably would work there too. So I'm not even going to say those would necessarily be. So again, if you need them, here they are. If you don't sweat it. Okay? Now, here is something, and I meant to say earlier, let's see, how many of you have turned in the research papers yet? Oh, none. Okay. And how many have turned in the first test yet? None of those either. Okay, so it's almost midterm, folks. And now technically here is something that Lawson does that I don't know if your school does, because we sort of mollycoddle and spoon feed a little bit. If people have D or F at midterm, we report that so someone gets in touch with them and see what they can do to help out. Well, since midterm is coming up Thursday, okay, sometime next week they may open it up and say, where are your midterm progress reports? I'd like to have some scores in on you so I don't have to say, oh, this person's failing at midterm. Not that it matters any. They'll just try to get you a tutor or something. And if you want one, good, go for it. But you can do that on your own. You don't have to wait for them to search you out. So try to get something in. But the reason I said that, here is someone who could be a potential paper topic. In fact, I mean, he could almost be a dozen potential paper topics. Leonard Euler, probably you may have heard of him and be familiar with him, but you know, everybody hears of Newton and Leibniz and stuff. Euler probably did almost as much, or I mean, they say he ranks among the greatest mathematicians of all time. Okay, and you have dealt with him before. His work, printed in more than 70 volumes. Goodness gracious, this guy was prolific. Contains fundamental contribution to almost every aspect of mathematics and physics of his time. The French mathematician Pierre-Simon de Laplace, who's another person you could write on too, once declared, read Euler, he is our master of everything. If you've ever wondered where the E comes from for our base for the natural number, he came up with it, and it was given the letter E after Euler. Okay, trying to say for sure, is he the one that came up with function notation? I think he was. I think he may be the one who really did a whole lot. Well, I mean, just about everything. There's certain equations. One in particular is referred to as Euler's equation, and it's one of the simplest looking equations you'll ever see, and it has in it E, I, pi, yeah, and -1, yeah. Huh?
-1 equals 0, but then you could...
Yeah, the E to the I, yeah. It's just an incredibly simple formula that uses every one of our imaginary number, our pi, our E, these two irrational numbers, and I mean, it's just incredible what he's done. in just about every field you run into them. So, great paper topic. Not just him, any one of those areas that he contributed would be a potential paper topic. That's why you said you probably get a dozen papers out of this if you just chose a different feature of his. Or Laplace, who was a pretty good mathematician on his own right. But the reason they came up with him here is, in fact, I think his equation shows up. Yeah, e to the I pi is equal to -1. There it is. Euler's formula is e to the IT is equal to cosine t plus I sine t, which we use big time in differential equations. Yeah.
For the research paper, what are the requirements for it?
Okay.
What do we have to write about?
You choose the topic. That's what I say.
No,
Here's.
does it have to be like a 5-paragraph essay?
Okay. Okay. Not necessarily. You can do that if that's the form you like. You can go for that. All I said between 1 and 2 pages is all I require, but you can certainly be longer than this. But I'm looking for at least 1 to 2 pages of text. Now that doesn't include your header or things else of text. Once you start typing here, then go all the way to on the next page, at least that far. That's a page of text. Between 1 and 2 pages of text, whether that's 5 paragraphs or 3 paragraphs, whatever, you know. And double spaced. I want it double spaced. It's not that's optional. I really prefer it double spaced, even if it has to be 3 or 4 pages. You know, I want it double spaced. And you know, standard pitch font, you know, that kind of stuff. And pick your format. I don't care what format you use. Just be consistent and stay with that format. And pick your topic. Go for it. You know, just but. The other thing, for instance, that thing we just saw, the blurb that's in your book, that can't be your source. You may get the idea from here. You go get sources outside the book. Preferably something from the library or that you can get from the library, journals, magazines, yeah. But you can use internet sources if you're sure they are reliable sources, not just someone spouting off, you know. So. Yeah, if you go back, the first day of class, first day of class I went over the whole thing, and it's also out there on Blackboard, the written instructions, so they're all there. All right, so I'm not requiring any exercises from 7.4, okay? Let's move then to, okay, these were just a few other slides in 7.4. For some reason they jump into differential equations, which is a different course, so I'm not going into that now. There is one form, well, again, a solution for that differential equation. Here's where they bring up I and get that into the picture. That leads to Euler's equation, which is this, and no, it isn't. Well, they don't have it written right. Sorry. I don't want to say this and say use this. Don't use this. What you need is an I right there. Oh, no. Okay, I'm sorry. They left the A and B. Later they'll show that A is equal to 1 and B is equal to I. Sorry. There is Euler's equation, or formula it's called. This is called Euler's formula, which is useful in differential equations and other places as well. And there's Euler's, what is often called Euler's formula. Okay, they have a name for it, but it's just one of the most elegant, simplest, and amazing little equations you could have. And sure enough, it turns out being absolutely true. Okay. And that's it for 7.4. Again, nothing there is required of you. If you ever need any of that, there it is. Okay, moving on to 7.5. I've got to close this out. Okay. 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 7.5 is another technique of doing integration when you can't get anything else to work. And this is called the method of partial fractions. And this is jumping way ahead of where we are. In fact, I don't even see this in our edition. This is in the previous edition. No, it's an equation at the top of page 399, but we'll get there in a minute. This is the first slide, so when you're integrating a function, and basically the name of this function is called a rational function, f of x is equal to p of x over q of x. That's called a rational function. Why? Because it's the ratio of two other functions. But these two other functions are a special type of function as well. If you see capital P of x, what do you usually think of? What class of functions? Yeah, it starts with P. Polynomial functions, exactly. And since they already use P, Q will be the next one. And they also tend to capitalize polynomials, function names. I don't know why, but they typically do. So what a rational function f of x is a ratio of two polynomial functions. Of course, you've got one little caveat that you always have to consider, that you can't include any values for x that would make your denominator 0. So your domain may be limited here. But remember, with polynomial functions, usually all real numbers is your domain. So the only things you have to exclude are the zeros in your denominator. Okay, and you know how to find zeros in a polynomial that you did in pre-calculus algebra. So you just exclude those values, and other than that, you can find this is going to be a technique for integrating rational functions. Okay, and the title of it is the method of partial fractions. Okay. The idea here is to write this quotient, this ratio function, as a sum of simpler rational functions that can be integrated directly. Okay? That's the idea. Now, for instance, what if you had 1 over x squared minus 1? Okay? Now, if that was a radical x squared minus 1, we just did that. That was a trig substitution. But without the radical there, we could maybe use a trig substitution, but why would you want to? Let's see if we can write that in a simpler form. If we were trying to integrate that, no substitution would work except possibly a trig substitution. But because that is a rational function, ratio of two polynomials, the top polynomial is pretty simple, but the bottom polynomial isn't too bad either. What would you do if you're trying to simplify this? What would be one thing you would do? That sounds like a capital idea. How would you break that up? Times x minus 1. Okay. Now, if that's your denominator, and you're trying to get a simpler form of that, doesn't it sort of stand to reason that there should be some numerator that you could write as, say, a over x plus 1 plus b over x minus 1? Yeah, okay. It should work, because what you would do, least common denominator of these two is that one, okay? And then you would have a times this plus b times that. Yeah, and then you want all that to equal 1, right? Yeah, that's the process that we're going to use here. with a few shortcuts, okay? Some of these shortcuts don't even seem like they should be allowed, but they do, and they work, and that's why they're allowed, because they do work, okay? Let's see what we get if we were to do that. Wouldn't this suggest to you, if you get it back to this form, this would be a times x minus 1 plus b times x plus 1 over x plus 1 times x minus 1. If you use the common denominator of that and then multiply. Okay? Now then, just looking at this, that would imply that ax plus bx, you see an x over here? No, so that coefficient has to be 0. So that would suggest a plus b is equal to 0, right? Okay, let's write that down. A plus b equals 0. And then we also see that minus a plus b should equal to 1, right? So in other words, b minus a, b minus a is equal to 1. Or let's go back and set it the other way. Minus a plus b is equal to 1. Guess what? I think we can solve that system of equations, can't we? Just add the two equations together. What do you get? Add these two. The a's go out. 2b is equal to 1, or not 2b, okay? B is equal to 1/2. And then this tells you that a is equal to minus b, so a would be negative 1/2. And sure enough, that would work. So here we could break this one that we can't integrate into negative 1/2 over x plus 1 plus 1/2 over x minus 1. And guess what? I think we can integrate this, right? And we can integrate that, right? This is going to be the natural log of that. This will be the natural log of that. Well, minus 1/2 is the coefficient, plus 1/2 is the coefficient. Yeah, so those are easy to integrate, whereas that one is basically impossible to integrate. So that's sort of a thumbnail sketch of how we are going to do these. Well, look, they did it. I didn't realize they were. Okay, dx here, and here. This integral would be equal to that integral plus that integral, which would be minus 1/2 times the natural log of x plus 1 plus 1/2 times the natural log of x minus 1. And you have to put absolute values because you don't know what the restrictions on x are, so you have to make sure that's only taking logs of positive numbers. Okay. Now, I think you can look at this and say, well, certainly x can't be minus 1 because you can't take a log of 0, and x can't be positive 1 either because you can't take a log of 0. Look at here. X can equal plus or minus 1 anyway, because that would be divided by 0. Okay, so sure, you're okay, and frankly, remember rational functions. I said you have to exclude the places where your denominator is 0. 0 is the denominator. So basically, you don't have to graph it in gory detail, but at least you have to identify this is vertical asymptote x equals negative 1, vertical asymptote x equals positive 1. It's doing something over here, something in between, and something over there. If you're doing an integral, you got to make sure you don't cross either one of those vertical asymptotes because you can't do that. Those are not defined there. So your limits, if you had limits on the integration, they have to both be less than negative 1, between minus 1 and plus 1, or greater than positive 1. They would have to be. And then your answer makes sense too. okay? And if the x was less than 1, then you do the absolute value, because this would be less than 1, and that would be less than 1. If between plus or minus 1, you do that. If it's greater than 1, lose the absolute value bars, because both of those are going to be positive. Okay. So you see your domain, which comes basically out of your denominators there, are going to dictate some of your answers sometime. It all works out. Okay. Now, before we get too much further here, let's get a couple definitions for you. I guess I will erase all this, but I'm going to rewrite one of them. Okay? This rational function f of x equal p of x over q of x. Couple of definitions for you here. Let's go back to fractions. We love our fractions, right? If I said a fraction was proper, what does that mean? When it drinks its tea, it keeps its pinky up? No, that's not what it means by proper.
It means that you've divided out all that you can from the numerator into the denominator.
Okay.
And to make it into
Okay.
a mixed fraction. Isn't that?
Yeah, okay.
Okay.
It's proper if the numerator is less than the denominator.
Right.
Okay? Improper if the denominator is greater than or equal to the numerator. Wait. Numerator is greater than or equal to the denominator, right? Okay. Well, the polynomials think sort of the same thing, except we're not thinking value here, we're thinking degree. If the degree of this numerator polynomial is greater than the degree of the, or equal to the degree of the denominator, divide them out. Synthetic division, long division, whatever it is, divide them out. Okay? If, however, the p of x has less degree than the q of x, then proceed with your partial fractions. It will not work if this p is greater than or equal in degree to the q. So first divide out if p has a greater degree than q, okay, or equal to. Okay. Now, another requirement is q of x has to be factorable, okay? Now, not all polynomials are factorable, but this means factorable even using irrational numbers, okay? So in other words, do whatever you can to get this, break this into either linear or quadratic factors, even if those factors contain irrational numbers, but not complex numbers, just irrational numbers, no i's in there, okay? So you should be able to factor this into that, even if you have to use radicals, okay? So I think there we have, okay, let's give just a few examples of this. Here is a polynomial, is a rational function. X squared minus 3x plus 7 over x fourth minus 16. Is that a proper rational function? Yay or nay? Yes, it is. The degree of the numerator is only 2, the degree of the denominator is 4. Okay? Now, the next thing that's required, the denominator needs to be factorable. And that one is, at least to a certain extent, what would that factor as? Okay, x squared plus 4 times x squared minus 4. Now, the x squared plus 4 can't be factored any further, not with real numbers. But that's okay, it's a quadratic. The x squared minus 4 can be factored one more time, x plus 2 times x minus 2. So that's okay. that will work out fine for us, okay? Now here's another one. 2x squared plus 7 over x minus 5. Is that proper? Huh? Improper. So what would be your first step here? Say again? Yeah, divide the x minus 5 into the other thing. That one you could use synthetic division, because the key for that is in your denominator, the numerator needs to be 1 with the exponent 1. As long as you got that, you can use synthetic division. 5 will be what you use on the outside and do it with that. And remember, you have to interject a 0 there for your x term, you know, that kind of stuff. But yeah, that can be done, okay? Get it into a proper form, and then once you get it there, you don't even need partial fractions. The integral of that next part, the last part, is going to be log x minus 5, whatever your coefficient is, okay? But yeah, you can't use anything there. How about this? X minus 2 over x minus 5. Is that proper or improper? Improper, because they have the same degree. Again, divide. Now this one, yeah, you could use synthetic division because the same rule applies. Or you could use long division. It's pretty simple. But then at the end, you don't need to use partial fractions because that's already, that last integral is going to be log of absolute value x minus 5. Okay. Now, all right, we're going to start with the ones that you can factor completely. That one you'd have a quadratic left over. We want to get only linear factors, okay? And we're going to start with problems like that. And let's just do one. You're like, well, hit the wrong key. Okay. Oh, got 5x squared plus x minus 28. Now they've been very nice to you here. Divided by x plus 1 times x minus 2 times x minus 3. First, is that proper or improper? Improper, why? It's proper because the degree of the numerator is 2 and the degree of the denominator, they've already factored it for you, but if you did multiply through, you'd have an x cubed down there. So that would be proper, okay? Now, thank you very much. They already did the denominator for you. So what if you were trying to do, and here's the procedure, by the way, just like before, a over x plus 1 plus b over x minus 2 plus c over x minus 3. Okay? Now, here's the step you use to do this without having to do solving systems of equation. This is the easier way. Multiply both sides of the equation by that factored denominator. Okay? So this thing would be multiplied by x plus 1 times x minus 2 times x minus 3. This is multiplied by x plus 1 times x minus 2 times x minus 3. This is multiplied by x plus 1 times x minus 2 times x minus 3. My writing really stinks, doesn't it? This is multiplied by x plus 1 times x minus 2 times x minus 3. Okay? Now, the good news is all your denominators disappear. That's always good news, isn't it? All three of these go out. Okay? So you're left with 5x squared plus x minus 28 is equal to. Now on the right hand side it got a little messier. Okay? You got rid of denominators, So the first one is a times x minus 2 times x minus 3 plus b times, here the x minus 2's go out, x plus 1 times x minus 3. And here the x minus 3's go out. They've been dating, okay. That's plus c times x plus 1 times x minus 2. Okay? Frankly, even though the right-hand side, which was looking rather simple, the left-hand side got much simpler. The right-hand side, you lost the denominator, picked up a bunch of fractions. Okay? Now, here's the trick that doesn't seem like it should happen, but it works, so it can happen. Let's pick an x value that's going to help us on the right-hand side, like maybe x equals 2. Now, if you go back to the original thing, x can't equal 2, okay? But written this way, you can get away with, let's say, x equals 2. That doesn't seem fair. I admit, it doesn't seem fair to use a value that you can't use. But let's do it. Well, when you use x equal 2, so when x is equal to 2, what's the left-hand side? Can you do that? Five times 2 squared would be 20. 2 minus negative 6. So there's your left-hand side. What's your right-hand side of the first term? 0. Last term? 0. And what's your middle term? 3 times, so it'd be negative 3b. Guess what? b is equal to 2. Right? Because negative 6 is equal to minus 3b. Boy, can you get much easier than this? Okay. Let's go to the next one. Let's let x, you can tell me what you want x to be. Oh, easier. 3. Let's x equal 3. What does it become here?
45.
That's 45. 20. Okay. And over here, now, just for funsies, since I can do this, I'm going to wipe out those and start with the clean slate. X equals 3, and what do you get? 0 for, well, no, a's not 0, but that a term is 0. This term goes to 0, and that leaves you with 4. Is that right? 4c. And guess what c is? Second, 5. Okay. And can you give me another x you want to use? 1. Oh, where did that come from? I don't think so, but x equal
2.
close to 1, but not quite. Negative 1. Good. What does the left-hand side become? Well, this is the easiest one. 5 minus 1 minus 28. Maybe it's not the easiest one. Negative 24. Okay. Is equal to, and let's go back. I'm going to use the same one so I don't have to rewrite it. Okay. And what happens if I use x equal negative 1? That the second one goes to 0 and the third one goes to 0. And what does that give you here? Yeah, okay. Minus 3 times negative 4 is positive 12a. So guess what a is? Negative 2. So let's see what we've got here. We've got this messy looking expression here without the things crossed out is equal to negative 2 over x plus 1 plus 2 over x minus 2 and plus 5 over x minus 3. Okay? So if we were integrating that, that would be the same as integrating these, and that would be minus 2 times log of x plus 1 plus 2 times the log of, natural log of x minus 2 plus 5 times the natural log of x minus 3. Okay? And you probably have a plus c somewhere in here too. Okay? If you didn't have limits. Okay? But now you have to remind yourself x has to be to the left of negative 1. It can't be negative 1. It has to be, it could be between minus 1 and 2. It can't be 2. It could be between 2 and 3, but it can't be 3 either. Or it could be anything greater than 3. And depending on where you are, if you're integrating and it's within limits, the limits can't cross one of those vertical asymptotes. Cannot. So it could be between negative 10 and negative 2, no sweat. You can integrate there. Between 0 and 1, you could integrate there. Between 2.1 and 2.9, you could integrate there. Or anything beyond 3, you can integrate. From 3 to 17. Not 3. From 4 to 17. Or whatever you want to choose there, you could. And depending on your choice there, you could drop some of the absolute values here. Otherwise, you have to keep those that would be negative because you can't take log of a negative. Okay? So you see, did you want to try to integrate that before we started this? I wouldn't either. Okay. Not on your life. Okay. So let's go to the actual first example. How are we doing? Yeah, we got time. My throat's going on me again. Sorry. Here is the first example. Integrate dx over x squared minus 7x plus 10. Okay? Now, just a couple sections ago, earlier today, in fact, we did something like completing the square of that denominator, and that was a lot of fun, wasn't it? Yeah, I thought you thought so. Let's see if maybe we can avoid that this time. And so let's see if it's any more fun. Okay? Could it be? So where would we begin? Say that again.
It would be 1 over x minus 2.
Very good. He factored that denominator. That's a good thing to do when you're doing partial fractions. If it's not factorable, then go back to completing the square or something. That one's factorable, go for it. And what would you like to set that equal to? Showed you the pattern, you tell me what. Sounds good. B over x minus 5. Very good. Then the next step would be multiply, clear your denominator. X minus 2 times x minus 5. 5. Okay? Multiply this one by x minus 2 times x minus 5. Multiply this one by x minus 2 times x minus 5. Legal, right? Do the same thing to both sides. Okay. And here, with sound effects, all your denominators go. Over here, x minus 2's go, and over here, x minus 5 go. Okay? So that leaves us with, I'll write it a little neater, 1 is equal to a times x minus 5 plus b times x minus 2. What might you choose? X equal what? 2. Okay, let's do that. And what do you get here? Nothing changes there. 1 still 1. And here what you get? Now the 2 goes to 0, so the b term disappears, and you get, second?
Negative 3a.
Yeah, negative 3a, which means a is equal to negative 1/3. Okay? What would be the next thing you might want to try? Okay, and I will go up here and take off that so I don't have to write it again. I'm that lazy. And what happens here?
Goes to 0.
The first term goes to 0, and that leaves you 1 is equal to 3b. So b is equal to 1/3. So now we can rewrite that integral as negative 1/3 times the integral of dx over x minus 2 plus 1/3 integral of dx over x minus 5. I think we can do both of those, can't we? Integral of dx over x minus 2. Natural log of absolute value x minus 2. Next, plus 1/3 natural log of x minus 5 plus c. Don't forget your plus c. You don't have to do one for each one. Just make sure you got one. Now, here comes the magical part. You can write this answer in several different ways using rules for logarithms. This could be written as the natural log of absolute value of, goodness gracious, I can't read my writing, x minus 2 to the negative 1/3 power plus the natural log of x minus 5 to the positive 1/3 power, which you could write as, if you, the natural log of 1 over the absolute value of x minus 2 to the 1/3 power plus the natural log of x minus 5 to the 1/3 power plus c. Let's see. You could write that as the log of x minus 5 over x minus 2 everything to the 1/3 power plus c. And you could write that as a cube root if you wanted to. There's a bunch of ways to write that. Okay? Let's see what they left it exactly in our first method. They left it in, I had it in my vision, now I can't see it. There it is. This is how they left the integral right here, with the plus c in it. Okay. Yeah. Okay, so they didn't try any of the fancy stuff to simplify it. And that's the problem. Sometimes the book does and sometimes it doesn't, which is also, if you're using some of these computer-assisted, web assign, those kinds of things, then they won't, and answer, and there's about 3 or 4 different perfectly good forms you can write that answer in. It would tell you every one of them was wrong except the one they were looking for, and you then have a guessing game to see which one they're looking for. You may run out of, depending on how the instructor set it up, how many chances you get to make a guess whether you get it in time. All right. Now, if you'll notice here, our statement right here, 1 is equal to a times 1. Okay. Kind of this first one, if you cancel out the 2 over here and cancel 2, so you just have 1 on this side and have x minus 2 times x plus 5 times this thing here. There's that first step. And then the next step is 1 is equal to a times x minus 5 plus b times x minus 2. So there's those steps there. And I think they actually show some more. Yeah, this is then, once you found the a and the b to be minus 1/3 and plus 1/3, then this becomes your new integrands. And now they might go to a different problem. So it's kind of weird how this book does its thing. Okay. Any questions on that? Was a pretty simple one. It was easy to factor that denominator and then just setting up and going from there. Let's do example 2. Let's evaluate this integral. X squared plus 2 over, they factored it for you. Thank you very much. X minus 1 times 2x minus 8 times x plus 2 dx. Now, frankly, I find this pretty obnoxious. And here's why. Why do they have a part of the denominator that's so easy just to factor out the 2? And then the whole problem is pretty easy after that. But they do it this way, and it's just a lot messier. So I'm not going to do it that way. I'm going to factor out the 2. But you have to keep up with it then and make sure you don't forget it, that it's there. It also changes how your answer looks, but it does come up to an equivalent answer. So I found it totally obnoxious for them to do something like that. So I think I'll rewrite this as 1/2 the integral of x squared plus 2 over x minus 1 times x minus 4 times x plus 2. That's a plus. It's ugly plus dx. Okay, you tell me what to do next. Second?
X squared plus 2.
X squared plus 2. I'll write all that, okay. Okay. Okay, you want, okay. Sometimes it picks up the eraser and sometimes it doesn't. Okay. I think that's a +2, isn't it? Yeah. Okay. I'm just going to do it like this if it's okay. I probably ought to fill them in. Yeah. X minus 1 times x minus 4 times x plus 2. Okay. Here, all these go out. Right? Here, the first one goes out, and that leaves the x minus 4 and the x plus 2 here. Here, the x minus 4 goes out, leaving an x minus 1 times the x plus 2. Here the x plus 2's go out, leaving those two. Okay. Next. Well, we rewrite that just so it looks a little better. X squared plus 2 is equal to a times x minus 4 times x plus 2 plus b times x minus 1 times x plus 2 plus c times x minus 1 times x minus 4. Okay? Next. -2. Okay, if you want to start there, that's perfectly fine. That goes to 0, that goes to 0, and that gives us I thought you said let x equal -2. -2 squared is 4 plus 2 is 6. Okay? Equal.
Yeah, I went ahead and did the other side.
Oh, okay. Oh, I see. Okay. All right. So this will be
-3
5
times -6.
Okay, but I think that's oh yeah, okay. X equal -2, yeah. -18 positive 18c. Okay, got it. So that implies that c is equal to 1/3. Okay. Next.
Let x equal
+1. Okay. Let me erase that. Okay. And what would that yield? 3 is equal to, and here that goes to 0, and that goes to 0, and that leaves us with, second, okay, 3 minus 4 is -1.
We're putting in 1 positive.
Oh, I'm sorry, 1. I'm sorry, I'm looking at the wrong place. Yeah, that'd be, yeah, -9, A, huh?
A, yeah, and then that would give you -1/3.
A is equal to -1/3. Okay, and the last one is let x equal 4. So the right hand side becomes 18 is equal to, and let me get these cleared out of the way. Okay, that goes to 0, and that goes to 0, and this is equal to, what'd you say?
18b.
18b, positive, right? Okay, so that implies that b is equal to 1. So now our integral, this up here, becomes 1/2 times the integral of, well, I probably need to do some other thing. Let me this is where you have to be careful, not get too carried away. Okay, going to pull that 1/2 outside of everything. Okay, and I'm going to write down this term, which was a was a negative 1/3. So negative 1/3 times the integral of
dx over, or we write in that form.
Yeah,
dx
there it is. Dx over x minus 1, right? All right. Okay. Plus, and that's just going to be a 1, is your b,
and that's
dx over
x minus 4
x minus 4
plus
plus 1/3 integral dx over x plus 2. Okay. Which is going to yield. Alright. The first one's going to be a negative 1/6, the log of
x minus 1
absolute value x minus 1, or 1/2. Okay, plus 6. Wait, I can't write. Okay. X plus 2. I can't read my writing. Plus C. Now, you'll notice, if you do, in the book, they came up with different A's, B's, and C's because they left the 2's and the 4's in there. So when they finally got an answer, it's a minus 1/6 log x plus 1. That came out the same. But then they have a plus 1/2 that, which would not seem like it would be the same. So it's, you know, it doesn't look the same, but those do turn out being the same answers, by the way.
That's crazy how
It really is.
you end up getting negative 1/6 in front
Right.
of A and C, but B
Right.
would be.
I know. And I've struggled with that it wouldn't, but you see, whatever you put there, the value, let me just make sure that we didn't leave off one. I don't think we did. And their B turned out 1, 2, and ours did 2 because we got rid of that term. You know, so anyway, it does work. All right, I think I've run out of time, unfortunately. Okay, we'll start example 3 next time, and a few homework exercises in this section. You can do any of the odds, or do 1 and or 3, either 5 or 7 or both, and then do 9. I think that's probably as many as you can do. You probably could do more of them, but I'll just leave it at 9. We'll come back and do some of those others next time. Okay, good deal. Any questions? We will see you Wednesday. Last day before? What's that? Okay, let me see what I can see quickly here. I hit the wrong thing here. Here's what I meant to hit.